So epoxides are the three-membered ethers, three-membered ring, okay, cyclic ethers. And in this one, we're going to do everything about epoxides, which is the nomenclature, synthesis, and reactions. So first, as usual, what is an epoxide? And in this case, this is the nomenclature also, because epoxides are three-membered rings like this. They were called oxirane. Can also be called ethylene oxide. Very specific, actually. That's it. When you say epoxide, it means a three-membered ring. That's it. Everything else is going to be a cyclic ether. So four or five-membered ring is called a cyclic ether. Epoxide is very specifically a three-membered ring, okay? So here, for example, in this one, the last structure that we have here is 1,2-epoxy cyclohexane. So on the cyclohexane, on the 1 and the 2 carbon, there is an epoxy group. That's it. So it's not such a complicated nomenclature per se, and I'm not going to do anything more. The only thing I want to mention here before I move on is that an epoxy ring is always going to be a cis. Okay, so if you see here, both these bonds are going back. They could be coming to the front also. They could be wedges also, okay? But the thing is, you cannot have a trans ring, because if you have a trans, then that would be a very highly stressed out ring, poor thing, because one bond is going to the front, one is going to the back. That cannot exist, okay? So that's the only thing I would like to mention here. Let's move on. And moving on to the synthesis, okay? So there are going to be 2 or 3 syntheses that we do. I think 2 maybe. And the one that you have done also before in alkene reactions is making an epoxide using peracids, okay, which the one that you use was MCPBA, which is metachloroperbenzoic acid, and this is the structure. And I would like you to see something here, okay, so that you understand what is the point of the per. The per actually means maximum number of oxygens, okay? So for example, you have H2O and then you have H2O2. So this is water or dihydrogen oxide. This is hydrogen peroxide. Peroxide meaning per many, as much as possible oxygen. So the per acid means that you have as maximum oxygen as possible, and that one oxygen more is what we need here. Okay, so this one here, if you see, there is one oxygen here, one here, and then one here, right? So there are 3 oxygens. If I wanted to write the peracetic acid, I can write it like this also, CH3C, and then there is OOO, right? So CO. Oh my God, so many oxygens, right? So 3 oxygens I can write like that. Sometimes, people write like this also, CH3CO3H. It can be a little confusing because it might seem like, oh my God, there is a typo, but it's not a typo, it's a per acid, okay? So that's something you have to watch out for. See the reaction you're doing. And if that reaction calls for an epoxide synthesis or something like that, then yeah, it's a peracid, okay? Very rarely it can be a typo also, okay? But otherwise, peracids do exist. So the 2 common peracids are given over here for you, MCPBA and then peracetic acid. MCPBA, you should know the structure for it, because I can ask you, not I can ask you, I can give you the structure and expect you to know what this is. But you can write MCPBA for me. I also write MCPBA, okay, so that you know that I'm just referring to the perbenzoic acid. So what happens is that you take an alkene, you use the per acid, and you get an epoxide, okay? And so then here I'm just mentioning to you that you get a syn, kind of an epoxide, okay? Syn as in S-Y-N, not S-I-N. So there's nothing sinful about it. So in any case, you get, the epoxide only in one direction, okay? And this is the mechanism for this. I don't need you to know the mechanism. I just need you to know that this kind of a mechanism, you can see how many arrows there are going on here. And these many arrows, this means it's a concerted mechanism. Concerted meaning that everything is happening at the same time. You can't tell which was the first arrow I drew, because you cannot clearly see what's an electrophile, and where is my nucleophile? Okay, it's hard to see, although you can say, okay, this is the electron rich, so maybe this was the first arrow I drew, and maybe it was. I don't know, and you don't know, and it doesn't matter. Okay, so this kind of a mechanism, as I said, concerted mechanism. We're going to see a little bit more of it in organic too. These concerted mechanisms, and which are all like, happening all together at one time. Anyway, so that's the mechanism of forming an epoxide, okay? And this is the synthesis using an alkene and peracid. Another way of making an epoxide would be from using a halohydrin, okay? So a halohydrin, if you remember, was to take an alkene, treat it with bromine and water or chlorine and water, and then you get the bromine and the OH group, okay, on there, and you get them as anti, okay? If you remember, it was an anti-addition. So now that you have the alcohol and the halide in one compound, now you can treat the alcohol with the base, make an alkoxide out of that, and now you can have an internal SN2 going on, okay? So this internal SN2 will now give you an epoxide, okay? It will form a ring. It kind of looks weird, like this is possible. Yeah, this is possible, okay? Because here is the electrophile, here is the leaving group. So, but the only thing requirement for this one is that the alcohol and the bromine should be vicinal to each other in order to get the epoxide, okay? And the best way to make vicinal alcohol and the halide is right here, okay, using a halogen and water, okay? So a very nice synthesis of epoxide. You can use either of these syntheses. Both are fine. Neither of them have any kind of flaws, or I don't think there is any, any flaw in any of them. Okay, so the reactions for epoxides, we're going to do two reactions, okay, not two reactions, two types of reactions. One of them is nucleophilic type of a reaction, and the other one is electrophilic, okay, type of reaction. Both are kind of similar, okay, so that's why I kind of wrote on the top here, but we're going to do the nucleophilic mechanism first, all right? A nucleophilic mechanism means that you're dealing with a nucleophile to begin with, which means what? It means that your substrate is the electrophile. If you're reacting it with a nucleophile, your substrate is electrophile. Where is the electrophile here? Okay, in the epoxide, the electrophile is going to be the carbon, because oxygen is the electronegative group, right? So the carbon here is delta positive, carbon here also is delta positive, and I'm talking about these two carbons here, okay? So either of those two, any of those two, they are both electropositive, okay? So that's where the nucleophile is going to attack. So I've shown you the mechanism here at the bottom, and so you can see that this is going to be a backside attack. This is kind of like an SN2. So here this is a backside attack going on, and then the ring opens up to give an oxide, okay? Once you have an oxide, then you treat that with acidic water and protonate the alcohol. Again, 1 and 2, okay? Step number 1, step number 2. You cannot put the nucleophile in the acidic medium, okay? Otherwise, the nucleophile is going to just die, okay, in the acidic medium. It will just protonate using this water, and you will not have any reaction. So don't write them together. Make sure you write them as 1 and 2, okay? So the first step is nucleophilic attack. The second is the protonation. What does this mean for us? It means that almost any time you open up an epoxide ring, you're going to get an alcohol, okay? The other thing is you'll also get an enantiomer, okay, because you can have the backside attack from the back, on the backside behind the paper, and then in front of the paper also, okay? And so the epoxide ring is pretty much planar, all right? So you can have the attack from either side, and so you always get an enantiomer. You don't have to write the enantiomer for me, but you just need to know in your heart that there is an enantiomer, okay, forming, and the alcohol is forming as well. So then the question is, what are my nucleophiles? Okay, so since I'm doing all nucleophilic reactions, then what are the nucleophiles? Any kind of nucleophile, okay? So I have given you some examples here, but really honestly, you can have any kind of nucleophile. So I have a couple disclaimers, okay, over here, and I'll just say them to you. That first of all, and I think this is the main one actually, is that I'm not writing the second step, okay, where the alcohol is getting protonated. So that one is understood, okay, over here. And even you will see that in some of the worksheets that I have and study sheets and whatnot. Sometimes I don't write the protonating, okay, which is the acidic water, but it doesn't mean that you're not doing it, okay? A lot of times we don't write all the workup steps, but it doesn't mean that you don't form alcohol. You will form alcohol, okay? And the black one here, that's the alcohol, okay? All the blue ones are the nucleophiles. Okay. So here, the first one here is the hydroxide. Then here is the amide, and then here is an alkanide. So alkanide is triple bond. So, really like it's a nice big nucleophile. Here is, a sulfide. So, yeah, sulfide here. This is Grignard. So lots of different kinds of, nucleophiles here that are reacting. Okay, so and everything, the mechanism is the same. You get the trans stereochemistry there, so all of that is the same. Okay, so just kind of one thing to talk about, okay, with the epoxide, because in the previous slide, if you go back, I'm not going back, but if you see in the previous slide, I took a symmetric epoxide, okay, in there. Symmetric meaning that both the groups on this carbon, they were both the same, okay? In those cases, whether you attack on this carbon or this carbon, it doesn't matter. But in this case, I'm going to take an asymmetric epoxide so I can show you what happens, okay, when you have a nucleophilic attack. So when you have a nucleophile attacking, the nucleophile will attack the less sterically hindered carbon. Okay, that's the key thing if you have an asymmetric epoxide. So which means that the carbon on the left is not getting attacked, only the one on the right will. Okay, so the less sterically hindered carbon is the one where your nucleophile is going to attack. Everything else is the same, okay, so it's not an issue. It's just that where the first attack is happening. Okay, so in this case where you have a Grignard, in this case, this carbon at the bottom, this one is the less sterically hindered, so that's where you're going to see the group. Okay, so that's the key thing about the nucleophilic attack. So now we get to electrophilic attack. What does it mean? Electrophilic means that this is the electrophile that you're adding. Electrophiles for us usually have meant acids, okay? So electrophiles, acids mean something that doesn't have electrons, okay? So they have been positive, right? Electrophiles are usually positive, which means the epoxide is going to be the nucleophile here. Generally, what do we use here for electrophiles? Electrophiles are going to be water, alcohol. Both of those you will deal with in dilute sulfuric acid or phosphoric acid. You cannot use like HCl or HBr, okay? Not hydrochloric acids, not the halo acids. So we end up using dilute sulfuric acid and phosphoric acid. Your nucleophiles are generally going to be water and alcohol. Now, the reaction is sort of similar. If you look at this reaction, okay, so this is H3O plus water, means it's there, right? The nucleophile, you can see it in there as H2O. So which means that this is what you're getting, which means the ring is still opening, your epoxide is still giving you the alcohol. So that is all kind of similar, okay? So, but the mechanism is going to be different because now the epoxide is the nucleophile. Okay, so just a few things over here. In an electrophilic mechanism, the medium is always acidic. And you really need to see this, okay? So if I give you any reaction for epoxides, then you have to see whether I gave you an acidic mechanism or I gave you a basic one. A basic one will just have a neat nucleophile, which is negatively charged usually. If I give you an acidic mechanism, I will be writing H3O plus, okay, in there to tell you that there is acid in there, okay? So be careful, all right, because now the mechanism is slightly different. The mechanism starts from oxygen, which is now the nucleophile. So this picks up a proton, so it becomes an oxonium ion. Now the water here in H3O plus, I don't have any other thing here. So which means the nucleophile is water. So the water is now attacking over here. I haven't given anything else. Okay, that's why I know it's water. So here the oxygen now is attacking this carbon, which is the electrophile. Again, I have a symmetric epoxide here so far. And then this ring opens up, which is then the alcohol. So you still get the alcohol. Remember, in the basic medium, in the nucleophilic, you got an oxide. Here you don't get an oxide. You can see that over here in the entire mechanism, you don't have any negatives. It's either positive or neutral. And that's how it's supposed to be, okay? Any acidic mechanism, you can go back and look at alcohol. So you can look at this one, and future mechanisms we do. Everything, if you have an acidic mechanism, everything is either positive or neutral, okay? You can't have any negative things in here. So then the water attacks, you get the alcohol. Now the water here still has its extra oxygen. So then the water comes in, picks up the proton. Now we have our two alcohol groups. So we talked about this reaction way back in alkenes when we were talking about how to get a trans diol. This is how you get a trans diol. So back then we did not do the mechanism for the ring opening for the epoxide. So we just said, okay, we'll do it later, because at that time we were focused on just learning about how to make diols. Okay, so it was syn diol and trans diol or anti diol. So this is the anti diol. Now this is the mechanism. Okay, so here is another reaction, and this one here is going to be an epoxide using an alcohol. So here I'm taking an asymmetric epoxide. In the previous slide, when I was showing you the mechanism, it was still a symmetric epoxide, but this one is an asymmetric epoxide. And so here I want to show you that if you add a nucleophile, it will go to the carbon that is more substituted. So in the nucleophilic attack, it went to the carbon that was less sterically hindered, but now it is going to the carbon that is more sterically hindered, okay? The other thing I'm trying to show over here is that you're using alcohol as your nucleophile. So the medium is acidic because we are starting off with H3O plus, but your nucleophile is going to be the alcohol, okay, over here. So you end up getting a methoxy group on the carbon. So good way of making, ethers also. Anyhow, okay, so the mechanism is exactly the same, okay, which means that the epoxide will pick up a proton from the acid, and then now the alcohol is going to attack this carbon. And in this case, because this is an asymmetric epoxide, this carbon gets attacked. Now the question is, why does this carbon get attacked? So what happens in an acidic mechanism is that the substitution is more like an SN1 substitution. In a nucleophilic substitution, it was more like an SN2. So in SN2, the nucleophile does not like to go to the carbon that is more sterically hindered, okay, because it wants to have its own space. But in the case of SN1, what is more important is that the carbocation be more stable. So if you're looking at these two carbons, the top carbon is more stable as a carbocation because it's more substituted. And that is how we do this in acidic mechanism. Okay, so in acidic mechanism, things are a little bit different. And so an SN1 type of mechanism is sort of going on, okay, in there. So when you have this kind of intermediate, and now you're looking at these two carbons, you have to see which carbocation is more stable, this one or this one, and the top one is going to be more stable. So that's the one that the nucleophile is going to attack. It's not about steric hindrance anymore. It's more about carbocation stability. So then you have the alcohol attacking. The alcohol now has the oxonium ion. Another alcohol molecule comes and picks up this proton, and you get your methoxy group, okay, on there, or whatever alcohol you had in there. So the mechanism is similar to the one for water, in which you got an alcohol here. Here you are using an alcohol, so now you got a methoxy group, okay? Now, in case you're wondering over here that I wrote methanol or water, because really all you're doing here is deprotonation. So you can use either the alcohol, which is already present, or you can use water, which is also present because you have H3O plus, okay? So you might think, maybe you might think that, why is the water not being used as the nucleophile here? So methanol is a stronger nucleophile than water is. Okay, so the methanol will be doing the reaction here. Also, you will have more quantity of the methanol. Okay, so I wrote water here, but really you're better off using methanol, okay, to pick up this proton. So final word on making diols. Okay, so when you make diols, we have now learned different ways of making diols. So I just thought I'll put that on one slide here for you so you can see everything all together. So here's an alkene. You treat that with osmium tetroxide and you get a syndiol. You treat that with KMNO4 cold and you get a syndiol. But you treat it with MCPBA to get an epoxide, and then you treat it with H3O plus in an acidic medium, right? So then you end up getting a trans diol. Now you can also use hydroxide here, by the way, okay? And I have that in the slides before. So you can use either H3O plus or you can use hydroxide. So either electrophilic, nucleophilic, it doesn't matter. But the main thing is you're going to get a trans diol using an epoxide. Okay, so depending on what kind of a diol you want and how much money you have, because osmium tetroxide is expensive, you decide, what reagents you want and what kind of product you're looking for. And here again, just a little bit of a review to you for on one slide is the ring opening when you have a nucleophilic substitution and when you have an electrophilic substitution. So in the nucleophilic substitution, if you were using methoxide, that methoxide would attack this carbon because this carbon is more, well, easily available, okay, or less sterically hindered, okay? So this carbon is going to get attacked if you have a nucleophile like this, okay, negatively charged nucleophile. In an electrophilic substitution, meaning that you have an H3O plus, so now the mechanism is more SN1, so now the methanol will attack this carbon, okay? So you can see that depending on the kind of medium you use, you can change the location of your methoxy group. By the way, this is also a good way to make ethers, okay? So, feel free to use this and add this on to your synthesis of ethers if you want to. But anyhow, that's that. So one of the things about epoxides, okay, and that's it. That's the reactions of epoxides, all of them. Is that they're really great building blocks. Epoxides by themselves are okay, and they're not completely unstable. There are three-membered rings, and three-membered rings are generally not very stable. So which means that their ring opening is really quite interesting. And seeing what we have done in the previous slides, you can use different kinds of nucleophiles to open up the ring, and do so many types of reactions, with epoxides. So here I thought we'll just do, a few syntheses so you can see how we can use epoxides in synthesis. So here, this is a typical kind of a question you can get, how to get from cyclohexane to this compound, which is an acid. So the first thing, of course, you do is you see, oh my God, okay, I'm forming, not oh my God, but really, okay. So, you're forming a carbon-carbon bond. So wherever you're forming a carbon-carbon bond, at this point, you only have a couple choices. You don't really have that many choices, okay, for carbon-carbon bond formation. One of them is using the alkynes, and then one of them is Grignard. Okay, so you only have two major choices. But anyhow, so you know that you're going to be adding this group, okay, which is you're forming a carbon-carbon bond. So how do you get started? Especially with cyclohexane. Like, I don't have a functional group on there. So what do I do? How do I begin? Well, you have to add a functional group first. So the best way to add a functional group is just to do a free radical reaction. At least you get a halide. Once you get a halide, now you can do elimination, substitution, whatever you want to do. So this is how to get started, okay? And once you have the halide on there, now I'm going to go ahead and add magnesium to this because I want to add 2 carbons, right? So my 2 carbons that I'm planning to add are going to actually come from epoxide. Okay, so I make Grignard reagent. This is my Grignard, and now I have my epoxide ready. So this is what I do. Okay, so I have been doing synthesis for so long. I've been teaching for so long, but I still need to do this, okay, because if I don't do it, sometimes things can be a little bit weird. Okay, so here, this is my carbon anion. So I will always draw an arrow that this is what I want to do. Okay, so that way I know that this is the ring opening. This is carbon number 1, carbon number 2. I always number my carbons also. I didn't do it here because I want to talk about this. Okay, so you have the nucleophile, and here is carbon number 1, which means this carbon is attaching to this carbon. So this is carbon number 1, this is carbon number 2. 2 is the one that's going to have the alcohol, okay, on it. When you have epoxides, it's kind of nice to number your carbons because that way you know where the alcohol group is going to go. Okay, so before I go on and finish this synthesis, I just want to say one more thing, okay, about this particular reaction. In this particular reaction, using Grignard and using an epoxide, look at this, we ended up forming a primary alcohol. Okay, so epoxides are actually a very good way of making alcohols also, and adding 2 carbons at the same time, and primary alcohols for that matter. Okay, so anyhow, that's just a sidetrack, but it's really it's an interesting thing because we know when you're doing synthesis, it's a good way to add 2 carbons and a primary alcohol. Anyway, last step is easy step, KMnO4, which is just oxidizing the alcohol to give you carboxylic acid. Okay, now I didn't specify in here anywhere what you have to do in order to make this kind of a compound. So you can use anything. Okay, I'm using epoxide because I want to show you how epoxides can be used, but this is not the only synthesis, okay, for this compound. And if you come up with another synthesis and you want to send me that, that's fine. I will check that for you. Okay, and in my mind, I have another one, okay, that I can do. I don't want to do it right now, but I have another one that I can do to give me the same compound, okay? And that's the beauty about synthesis, is you can do a lot of things in different ways, okay? Or not different things, but you can do the same synthesis in 2 or different pathways, okay? And so, you know, you work with some other people who have a different thought process, so that way you learn different reagents and different ways of doing synthesis. Okay, so this is one example of how you can use epoxides. Here is a nice little web, and I like giving webs, you know, for practice sake also, and also in exams and such. So a web is, you know, you have a starting material, you have all the reagents in here, so you fill out all of these question marks. You know, what do you get from this? So you can see here is a nucleophile, here is a nucleophile, here is a nucleophile, and then you know, if you have the right product here, you can go on and then on and then on. Okay, so this is a series of reactions. I have the answers on the next slide, and I will go through. I mean, I'll just, you know, slide it through, but otherwise you should do this on your own, okay, and see if you understand everything, and then you can check your answers over here. I'm going to go through this quick, although I know you have the printout, but still, okay, try to do it on your own before you check the answers. Okay, and that's it. I think that's all we needed to do for epoxides, so we're done.